Okay. So we will continue our third topic, okay, which is on the machine foundation on pile. Okay, what we have discussed this morning is on the introduction on the soil dynamic and also on the shallow foundation due to the dynamic load. Okay. So now we discuss on the machine foundation, okay, where it is located on a pile. Okay, so we will look on two type of pile, which is end bearing, and also the other one is the friction. And for the friction, we will discuss on a group of columns. Okay. Okay. So as an introduction part, okay, this machine foundations design, okay, which is also known as machinery foundation design, is accomplished to protect the adjacent foundation of the structure from the vibration of the rotating or vibrating machines. Okay, so there are four types of machine foundation. Okay, the first one is the block type. Okay, okay. And then this is means that they have a solid type of machine foundation. Okay, then they have what we call as a block types. Okay, and the other one is the wall type. Okay, which is the machine rested on this type of foundation. And the last one is the frame type. Okay, actually, I will not go through in detail, okay, what is the difference between each type of the machine foundation, okay. So this type of machine foundation, okay, either can be rest on a shallow foundation or on a deep foundation, okay. So for example, for this one, okay, so this machine foundation, okay, is rested on a pile model, okay. So it depends on the capacity of the foundation itself. Okay, if the shallow foundation, okay, does not sufficient enough to carry for the vibration due to the machine foundation, so therefore the need of the pile foundation is there. Okay. So it's also possible that the subsoil conditions are such that the vibration of a shallow machine foundation may lead to undesirable settlement. Okay, so uh, this is the use of the shallow machine foundation. Okay, however, due to the subsoil condition, so it may experience a huge settlement or excessive settlement. Okay, so in many circumstances, the load bearing capacity of the soil may be low compared to the static and dynamic load imposed by the machine and the shallow foundations. Okay? So in that case, the design will then dictate consideration of the use of the pile. Okay? So actually, we want to discuss on how to design, how to determine the capacity for the pile foundations. So the example is more based on what is the foundation that is suitable to be used, okay, to cater for this kind of problems. Okay, so in that case, okay, the discussion is more towards the foundation itself. Okay, it should be keep in mind that the use of pile will, in general, okay, increase the natural frequency of the soil pile system, okay, and may also increase the amplitude of vibration resonance. Okay, so every system have their own natural frequency, and also may react on any vibration, okay, due to resonance effect. Okay, so in order to increase the stability of the system, okay, due to this kind of machine foundation. So that's why the application of file is very required. Okay. Okay, I will also include some explanation on the natural frequency and also some example of resonance on the other document. Okay, I will include in what we call it in the e-learning as well. Okay. Yeah, because if I want to amend this PowerPoint or slide, so it will take a longer time for me to upload in the e-learning. Okay. So I will include one document to explain on what is natural frequency and also what is the resonance. Okay. So this slide also I do some amendment. Okay, I will upload again. Okay, to replace the older version. Okay. So in general, files can be grouped into two broad categories. Okay. This is a typical type of file system. Okay, I guess all of you know that we have two types of system. The first one is the end bearing. This file penetrates through the soft soil layer up to a hard stratum or rock. Okay, the hard stratum or rock can be considered as rigid here. So it means that the tip of the file is rest on a hard layer. Okay. So another one is the friction pile or floating pile. Sorry, not plies. Floating pile. Let me. Okay, floating pile. Okay. The tip of this pile do not rest on hard stratum. The pile resists the applied load by means of frictional resistance developed at the soil pile interface. So means that you just can imagine it's a floating type. So it means that it not rest on the hard layer. Okay. So actually we have another type we call a socketed rock. Okay, rock socketed pile or rock socketed ball pile. Okay, which is I've not discussed it in this example. Okay. So we only focus on two types of pile system. Okay. Okay, for the end-bearing pile, the discussion is more related to the natural frequency of the pile itself. Okay. While for the floating type, okay, so we may consider the stiffness and the damping factor of the floating type. Okay. At the end, we can calculate what will be the capacity of the load that could be sustained by the system of the pile. Okay, so we go first for the end-bearing pile. Okay, the length of the pile is equal to L. Okay, and the load of the pile coming from the foundation is W. Okay, this problem can be approximately treated as a vertical rod fixed at the base. Okay, that is the hot layer. That is the rock layer, and free on the top. Okay. For determine the natural frequency of the pile, okay, three possible cases may arise. Okay. So there will be three types of cases that we need to consider, okay, in determine the natural frequency of the pile, which is depend on the weight that apply and also on the weight of the pile. Okay. For the case number one, okay, is W is very small, okay, approximately okay, relatively near to zero. The natural frequency of vibration can be given by following equation. Okay, so Fn is natural frequency of vibration equal to omega natural frequency okay, over 2 pi, okay, equal to 1 over 4L times square root EP yang modulus of electricity of the pile material over rho P density of the pile material. Okay, so we may use this equation, okay, to determine the natural frequency of the file for the case number 1. Okay. So then we have case number 2. Okay. If the W is of the same order of magnitude as the width of the file. So for example, if the file width is 20 and the W, the magnitude of the load, okay, is around the same order, which is one 10 to 100, okay. Or a little bit slightly bigger, okay. Should not greater than 200, okay. The question of the value can be given by equation, okay. Omega n and then include in the equation. Okay. So the equation can be A W. Okay. Sorry, W sorry W. This will be A. Okay. So that is for the case number 2. LP over sigma naught. Okay. Can you hear me? Hello?
Yes.
Sangkut, sir.
Sangkut,
Not
Doktor.
tracking doctor for case 2.
Okay. Okay. Okay, let me do something. Okay. Can you hear me? Is it better now?
Better.
Yeah.
Okay. So then either we use the equation here, okay, or we use this relationship to determine the omega. Okay. So the last one, the case number 3, okay, if W is larger and the weight of file is negligible in comparison, okay, then from equation, from this equation, okay, we can determine the value of the omega, okay, or we may use this equation, okay, to determine what will be the frequency. So the material value for the EP and gamma P, okay, we can use as listed in this table, okay. So or we can use this kind of what we call as a relationship, okay, to directly determine what will be the natural frequency for the case number 3, okay. Okay, so either we can calculate by using the equation, or we can just refer to this what we call as diagrams. Okay, but it depends on the type of the material that made of the pile. Okay, either steel, concrete, or wood. Okay. Okay. So we look on one example. A machine foundation is supported by 4 prestressed concrete piles. Sorry. Driven to bedrock. The length of each pile is 24 and they are 0.3 meter times 0.3 meter in cross section. Okay, so it is a square pan. Okay. The weight of the machine and the foundation is 1,360. Okay, so this is the W. Given unit weight of the concrete 24 and the modulus of electricity of the concrete used for the pile is 24.5 times 10 power by 6 kPa. Determine the natural frequency of the pile foundations. Okay. So this is the W. Okay. Then we need to compare with the width of the pile. Okay, to determine either it is case number 2 or case number 3. Because case number 1, I guess the W is very huge. Okay, or the W has big magnitudes. Okay, for it to be considered as a case number 1. Okay. So there are 4 piles there. The weight carried by each pile is 1,360 divided with 4. Okay, so the value is 340. Okay, so the weight of each pile. Okay, by knowing what will be the area times the length and times by the unit weight of the concrete. Okay, so then we can gain 51.84. Okay, so the length is 24, the cross section is 0.3 times 0.3, and the unit weight of the concrete is 24. Okay, so the value is 51.84. Okay, so from this example, okay, so the author used the case number 3, okay, which is he considered that the W and the weight of the pile is relatively have a same magnitudes as a comparison. Okay, so if the case number 3, okay, we looks like the W is very big compared to the weight of the pile. Okay, but for me, we cannot put in the case number 3. Okay, so that's why the author consider as case number 2. But I didn't have any idea in terms of what will be the range. Okay, for example, this is almost 6 times larger. Okay, and what can be cost for case number 3 to be considered. Okay, because case number 3, the W is larger and the weight of pile is negligible in comparison. Looks like it's very big compared to the case number 2. Okay, the W is on the same order of magnitude as the weight of the pile. Okay, however, the value is a little bit higher, which is almost 6 times greater. Okay, okay, but we just looks on this example first. Okay. Then the next step is to determine the, we may use this equation. Okay. Okay. So we want to determine the W. Okay, because at the end, to get the natural frequency is W over 2 pi. Okay. Sorry, not W, omega. Omega over W over 2 pi. Okay. So here we already have AL gamma P and then over W. Okay. 51.84 over 340. Okay. So we have there the length is 24. Okay. And then we need to determine the BCP. Okay. So what is the equation of the BCP? Okay. Here EP over rho PP, or we look on the VCP. Where is VCP? VCP. Okay. Okay. So actually the VCP is not, I forgot to provide the VCP. Okay. However, the VCP has been provided here, okay, which is the EP over rho P, square root of EP over rho P. Okay, what does it mean with VCP is the longitudinal wave propagation velocity in the file. Okay. So the VCP is 3164.6 meter per second. Okay, then put the value. Okay, then this is not all. The all should be here. Okay. Okay. Then this is the value for the to solve it. Okay, where we need to get the omega value. Okay. So there will be another way. Okay, by using the figure 11.2. Okay, which is the this equation. Okay, which is L times gamma P over sigma naught. Okay. So what is the sigma naught? Sigma naught is W over A. Okay. So we can get the W over A, where the W is 340, the A is 0.3 times 0.3. Okay. So we can easily get W over A to represent for the sigma naught. Okay. Then L is 24 and unit weight of the concrete is 24. So at the end, the value is 0.1525. Okay. So to get the omega L over VCP, okay, then we may use this equation. Okay. So the value is equal to 0.1525. Okay. 0.1525. So approximately here. Okay. So then we can get the value for the omega L over VCP, which is approximately equal to 0.36. Okay. So this value, then we multiply with 3164.4, which is the VCP, over 24. So the value for the omega is 47.5. Okay. Then from the 47.5, divide with 2 pi, so we obtain 7.56 Hz. Okay. So try to solve this equation, okay, by include 7.65, or you can calculate to get the value of the omega. Okay. So that is for the end-bearing type. Okay, where we may consider the natural frequency of the file system. Okay, so then we may compare with the value for the frequency from the system. Okay, frequency from the machine. Okay, does it is higher or less compared to the natural frequency of the end bearing pile? If greater, so we need to increase the number of the pile. Is lower, then there will be no problems in terms of the pile system. Okay. Okay.
I'm sorry, Doctor.
Yes.
Can you repeat the last thing that you just mentioned about why this frequency is being higher and lower?
No, I just say that we need to compare with the frequency from the machine.
Yes.
So let's say if the frequency of the machine is higher, then we need to do something to improve the natural frequency of the pile. If lower, if the frequency from the machine is lower, so there will be sufficient for the system to sustain the load from that machine.
Okay, thank you.
Okay. Okay. Yeah, because we didn't have the input of the frequency from the machine. Okay. Then we move for the friction pile. Okay. So figure below show a pile having a length of embedment equal to the L. Okay, so this is the L and the radius of R. Okay, the system is subjected to a dynamic load. Okay, which is the Q. So okay, this is the figure of B. Okay, this is figure of A. Forgot to mention here. Okay, this figure of B. Okay. So it is possible to idealize the pile to a mass spring dashboard system as shown in figure B. Okay. The mass M shown in figure B can be assumed to be the mass of cap and the machinery. Okay. The mathematical formation for obtaining the stiffness and the damping CZ parameter has been given by Novak 1977. Okay. In developing the theory, the following assumption we made: the pile is vertical, elastic, and circular in cross-section. It looks like um, when we want to determine the area, okay, we should use the circular cross-section. Although the pile, it is in round, it is in box, it is in square, okay. The pile is floating. The pile is perfectly connected to the soil. The soil above the pile tips behave as infinitesimal, thin, independent, linearly elastic layer. Assumption of plane strain condition. Okay. So I guess the rest information, okay, will be correct. Okay. Unless for the assumption that we should meet later on is on the circular in cross section. Okay, because there will be an example. They use a pile with a type of square, and then in order to calculate for the cross section, do not use the area of B, is the area of B times B, but need to assume as a round or circular type of pile. Okay. Okay, so this is the equation for the KZ and CZ. Okay. So where we can get easily the information of the EP, A, and R. Okay. And also EP, A, and G. Okay, R will be, R is not given here yet. Okay. Where is R? Okay. R is the pile of radius. Okay, so that's why we need to use the radius. Okay. Okay, so R is the radius. Okay, FZ and FZ1, FZ2, okay, is a non-dimensional parameter. Okay, so for this case, the FZ can be determined from this chart. Okay, which is the ratio of the LR. Okay, and the ratio of the EP over G. Okay. So we may use this, what we call as this diagram to get the value for the FZ1 and FZ2. Okay. So the example for the friction pile will be discussed in the group piles. Okay. Pile foundation, okay, so this is for group pile. Okay. Pile foundation are generally constructed in the groups. The stiffness and the damping, which is the KZ and the CZ, constant of a pile group are not simple summation of the stiffness and damping constant of individual pile. Okay. So Novak suggested that when piles are closely spaced, the displacement of one pile is increased due to the displacement of all other piles, and conversely, the stiffness and damping of the group are reduced. Hence, the stiffness of the pile can be obtained as the sum of the kz, okay, because this is a pi group, over the sum of the alpha r. Okay, so this is the alpha r, which is related to a spacing. Okay, we show you how to obtain the alpha r. Okay, where we need to do a calculation in the use of a graph. Okay, so while the CZ is obtained from the normal equation here, okay, later on we need to divide with the alpha r, okay, to get a CZ and KZ as a group. Okay. Okay, so this is the way to determine the alpha, okay, where we may refer to the 2 over as of spacing over 2r, okay. So while this is the length over 2r as well, okay. So later on, we may look on how to use these diagrams, okay. Okay. So for pi group, a cap is constructed over the pile, okay. In the estimation of stiffness and damping constant, the contribution of the pile cap should be ignored. Okay. The relationship describe the stiffness and the geometry damping of embedded foundation are given as below. Okay. So this is the equation, main equation, and then there will be an additional of the GS, DF, and also S1. Okay. So all this value we may refer to the number of to the value of the Poisson ratio. Okay. And then for the CZ as well, so CZ over alpha R plus DF R naught S2, which is this one, okay, over GS over rho S, okay. Okay, so to calculate for the damping ratio, okay, then we may use the dz over equal to cz t over 2 square root kz tm, where m is the mass of the pile cap and the machine supported by it. Okay, so then another equation, which is the undamped natural frequency, okay, omega n, okay, fn, okay. But to honestly, I also do not really understand, okay, on what is the undamped natural frequency, okay. And there will be some of equation, okay, which is I just put in the in this example, okay. Let's say if we try to get any additional value, okay, so we may use this kind of equation later on. Okay, so we have undamped, we have damped natural frequency. Okay, then we have amplitude of vibration at resonance. Okay, so then we have amplitude of vibration at frequency other than resonance. Okay, so at the end, if it doesn't provide for any example, so it's very hard to understand 100% on the equation that's been provided in the in the reference book by Das. Okay. Okay. So now we look for the last example. Okay. So just I will use the significant equation only. Okay. Not all the equation that's been provided in this slide. Okay. So our interest only to know what is the KZ, the stiffness, and also the damping value. Okay. So a group of pile is supporting a machine foundation as shown in figure 11.13. Okay. So this is an example. Okay. A group of pile. okay, where it has 4 square, okay, type of concrete pile, okay, with a spacing 1.5 between A and B, okay, and also B and C and D and C, okay. Determine KZ and CZ, okay, given EP 21 times 10 power by 6, okay, G 28,000 kPa, soil density or soil unit width 19, assume Poisson ratio of soil new is equal to 0.5, okay. Okay, so this is the equation that we may use later on, okay. So first we work with the equivalent radius, okay. Although the pile is in a square, okay. So then we need to find what will be the radius of the pile because we want to use the R, okay. So R is equal 0.3 times 0.3 over pi power by half, okay, or square root, which is equivalent to 0.17, okay. Then the length of the pile is 12, okay. L over R, which is 12 over 0.17, is equivalent to 70.6. Okay, given EP is equal to 21 times 10 power by 6 kPa and G is equal to 28,000 kPa. So the EP over G is equal to 750. Okay, so from there, we need to determine what is the FZ1 and FZ2. Okay, so to get the value of the FZ1, FZ2, so we may refer to this chart. Okay, that's why we calculate for the LR, then EP over G. Okay, so the FZ1 and FZ2 is equal to 0.034 and 0.06. Okay, so then we may calculate for the KZ, okay, 700, EP A, okay, and over R, okay, or EP A over square root G over rho, okay, times FZ2 to get the KZ and also CZ. Okay. So then for the EP, okay, then the value of the KZ is equal to 378 times 10 power 6, okay, while for the CZ is equal to 94.311. Okay, so that is for the CZ and also single CZ and also single KZ. We want to get what will be the group KZ and also CZ. Okay. In order to determine the stiffness and damping constant for group pile, okay, so this is the equation 11.15 and 11.16 can be used. Okay. However, okay, the alpha R needs to be considered first. Okay, so this can be done by using figure 11.10, okay, which is this one. Okay, so we may use this equation, we may use this figure to determine what will be the alpha R. Okay. Okay. So how to use the figure? Okay. So yeah, if you have two monitor, so they will be easy. Okay. Or if you want to the other way, you just print the graph and then you follow or you see the what we call as the example. Okay, how we obtain 1, 0.54, 0.48, 0.54. Okay, so for example, this is the A. Okay, so we look again on the diagram of the pile. Okay, so this is the A, B, D, and C. Okay, so for example, for A to A, okay, A to A, the value is equal to 1. Okay, so what does it mean? Okay, means that based on the figure 1110, okay, so the S over 2R, okay, S over 2R, okay, with the spacing is equal to 0 because at the point of A, so the ratio between S over 2R is equivalent to 0. So when we look on the diagram, the alpha R is equal to 1 for the A. Okay, so that's why it written as A. A equal to 1. Okay, so now we look on the B. Okay, A to B. Okay, A to B. Okay, so the spacing is 1.5. Okay, so we drop here as 1.5. Okay, times 2. Okay, while the R value is 0.17. Okay, 0.17. Okay, so I need to get calculator first. Sorry. Then we calculate 1.5 over 2 times 0.17. So the value is about 4.41. Okay. Now we look on the diagram. Okay. At the same time, we have the L over 2R. Okay. So L over 2R. Okay. So in our case, the L is equal to 12. Okay. And 2R is equal to 2 times 0.17. Okay. So 12 over 0.2 times 0.17. So 35.3. Okay. So then the value for the L over R is equal to 35.3. Okay. Then by the use of sorry, 1.54. This is 4.5. 4.5. Okay. Okay. Then the value is approximately okay, with the new, so we have here new, what will be our new, the Poisson ratio is 0.5. So we may refer to the solid line. Okay. So here, it's stated here, either the new 0.5 or the less new is 0. Okay. So in our case, 4.5, okay, then the what we call, sorry, the L over R is about 30 something, okay, 35. Okay, so we just guess the value of the alpha R is around 0.5 something. Okay, so in this case 0.45. Okay. Okay. Then A to C, okay, we have the A to C, okay, what is A to C? Okay, so A to C, so we need to get the distance of A to C, okay. So how to get the distance A to C? Okay, so 1.5 power by 1.5 power by 2 times 1.5 power by 2, okay, then square root. So the spacing is around 2.25. 2.25. Okay. So AD and AB will be same, okay, except for the AC. Okay, so AC, the R is 2.25. So then we need to calculate 1.5. The spacing, so the spacing 2.25, okay, over 2 times 0.17 equal to 2.25 times 2 times 0.17. So 6.6, 6.6, okay. Then for the L over R is 12 over 2 times R, is 35, okay. 35.3, okay. So then we refer to the diagram, okay. 6.6, okay, so it's greater than 5. So most probably we use 5, okay. And then the L over 2R is 35. So the value is less than the previous one, okay. The previous one we obtained 0.5 something. So for this case, most probably 0.4 something, okay. So okay, so they obtain 0.48, okay. And A to D is same, which is 0.54, okay. So then we repeat to the other. B to A will be similar to B to A, okay. B to B is 1, okay. B to C is similar, is 0.54, and also repeat until we obtain the value, which is the total value, which is 2.56, because it is a symmetry, all of the pile location, position. So the value will be same, which is 2.56. Okay. So then the value is equal to 2.56. Okay. So this value, 2.56, okay, will be put in the equations, okay, of of the equation, okay, to get the kzg, okay, where the kzg is equal to this okay, kzg or kzt, okay, this one, okay, kzg. Kzg is the group, while kzt is a total, include the pi cap, okay. So then that is for the kzg first, okay. Okay, to get for the kz pi cap, okay, and the cz cap, okay. So then we may calculate for the other equation, which is gs dfs and dfr not s to square root gsps rho s, okay. So from there, df is equal to 1.5, okay. So what does it mean with df? df is the height of the pile caps, okay. The height of the what we call it, the base to the surface, okay. And then we have the G, okay, G. Okay, S1, we need to refer to the table, okay, here, 2.7, where the Poisson ratio is equal to 0.5, okay, 2.7, and S2 is 6.7, okay. Okay, S2 6.7, 2.7, okay. Then R naught, okay, is equal to 2.1 times 2.1 over 5 square root. Okay, what is the R naught? So I need to find first what is the R naught. What is the R naught? R naught. No, we need to know what is the R naught. Okay. Okay, it is a diameter to R naught. So radius of the pile caps. Okay. So the radius of the pile cap is R naught. Okay, so what is the R dimension here? The pile cap. What is the pile cap? Oh, it doesn't mention on the pile cap. What is the pile cap diameter? So 2.1. Okay. So how to get the R cap? This is 2.1. Okay. The R naught. This is 2.1. The area of the pile cap. 0.3 times 0 plus 0.3 plus 1.5, 2.1, 2.1. Then we make into a radius. Okay. So that is for the R naught. Okay. So this is the radius of the pile cap. I will put a note later. Okay. So this is the height of the soil above the pile cap. Okay, above the base pile cap. Okay, then we can get the KZ. Okay, where the KZ is GS DFS1. Okay, 113.4. Okay, and then for the CZ 277.33. Okay, so the total KZ for the stiffness of the pile group. Okay, include the cap, include the from the cap. Okay, is equal to 704.03. Okay, and the damping value for the group of pile with the pile cap is equivalent to 424.69. Okay, so that is for the task number 1. Okay. Okay. So there will be a last example here. Okay. Refer to example, the same example. Okay. If the weight of the machine being supported is 70 kilonewton, determine the damping ratio. Okay. So the damping ratio equation actually here. Okay. CZ total over 2 square root KZ total M. M is the mass of the pile cap and the machine supported by it. So the M has been given as 70. Okay. So the weight of the pile cap. Okay. So we need to identify what will be the weight of the pile cap. Okay. Which is 190.512 kilonewton. And the total weight of the pile cap in machine is 260. Okay. So then we put the value in the calculation to determine the DZ, okay, the damping, where the value is equal to 0.41, 0.491. Okay. So that is the value for the DZ. DZ. CZ. Second. M. So the damping factor. Okay, because it is a ratio, so it doesn't have any units. Okay, that's why it doesn't have any units. Okay, so that's all for the machine foundation. Okay, so with that, I end my lecture for today. Okay, so until we meet for the next lecture on, is it on January?
Yes, on January.
Okay, and then I will upload for one assignment, okay, regarding this topic. Okay, it will be straightforward. Don't worry. Okay.
How about the assignment given by the
Ah.
Dr. Carol? We still have to proceed, is it, Doctor?
Yes. So nothing changed, but might be we may revise the coursework mark.
All
Okay.
right.
Okay. So, okay, that's all for today. I will upload all the recorded version and also any additional notes in the e-learning. I hope by this afternoon. Okay. So, thank you very much.
Doktor,
Yeah.
assignment tu group